Hello and welcome to our next webinar with the topic Monitoring and Data Logging. My name is Thorsten Reibel. I'm sitting here together with Jürgen Schilder as always, and we will share this webinar. Monitoring and Data Logging. What is behind this? So we will talk today about three different components called Monitoring Unit EUB, responsible for monitoring of KNX devices in a KNX installation. Then about the Fault Monitoring Unit SMB 1.1. It's for detection and processing of fault signals. Whatever it means, we will see it later. And finally, done by Jürgen, we will talk about the Data Logging Unit BDB 1.1. It's for detection of operating hours of any loads behind and for detection of switching cycles. So we talk about three devices, look very similar, but they are different, of course. They have different software functions. You see, every device will be connected only to the bus. There are no in and outputs. The main functionality is in the software of the device. We will start with a monitoring unit, EUB. This device is for monitoring of up to 100 KNX devices in one KNX installation. And what will be monitored? The devices, whether they are still existing, and we can also monitor, let's say, minimum functionality, whether the components can send or receive telegrams, whether they can communicate. So we cannot check the whole component. For example, if we have a switch actuator we monitor, we cannot say, is a relay really properly working? Is the contact still in work? Or if you have a push button with separate bus coupler, if you remove the push button, it's neither possible to detect because the bus coupler is still existing and the component can still work or communicate, though the complete device is not really existing anymore. But in most of the cases, we can really evaluate, is the device still properly working? We can do this in 4 different ways. We will see in the next slide. And additionally, we can integrate each device into a group in up to 5 groups. So in this case, you can get a kind of collective message if one of these members of a group has a failure. We come to this at the end of the description of this product. I mentioned already 4 different monitoring types, split into 2 main types: monitoring via physical address and monitoring via group address. And if you talk about monitoring via physical address, it's possible via polling the physical address cyclically, or polling the physical address by a communication or group object. If we do monitoring via group address, we can poll a group address cyclically, or we can receive from the device to be monitored cyclically a telegram. So we start with the first monitoring mode, poll physical address cyclically. With this mode of monitoring, the unit cyclically polls the physical address of the device to be monitored. So the EUB sends in this case a polling request to the device, and of course expects any response from this device. And if this is okay, the communication, the response came back, then everything is fine. And let's have a look to the next slide, where you can see how easy it is to adjust this in the parameters. So first of all, you can do this for each device individually. You can say, okay, device number 1, for example, shall be monitored via polling of the physical address cyclically. So you do nothing else but writing into the parameters the physical address, area, line, and bus number. Then you have to decide in which cycle time it shall be monitored. So in this case, every 10 minutes, communication will be established from the EUB to the device to be monitored. Additionally, we will see it later on as well, you can block this. You can say, okay, I don't want to monitor during a certain time. That's possible via another group object. Looking at these group objects, we have, of course, then for this device number 1, for example, a group object called failure. So in case of a correct communication to this device via physical address, here a telegram will be sent with value 1, indicating this device has a problem. Yeah, as already mentioned, we can block this monitoring for a certain time. It's a separate communication or group object here, and with value 1 sent to this group object, the polling of this device will be blocked. Yeah, in a more visual way, I would like to show how it works. In the middle is our monitoring unit EUBS. On the right side, you see here a switch actuator, and this switch actuator shall be monitored, for example. So the EUBS sends cyclically polling request to this device, means it sends a so-called T-Connect command. That's the same you have if you would like to download something to the device. And the device should normally react with a T-Disconnect response, if it's properly working, of course. And then component EUBS is happy, so it does not have to send any failure, and the same will happen another 10 minutes later, for example. You see here a push button on the left side. This could be used, for example, for blocking the communication to this device, as already mentioned. You see here the device 1 failure group object shown here, 0347. If there's no failure, value 0 will be sent back, but not all the time, because if it was before already okay, then it will be not sent back, only on alteration. So when before this the situation was a failure existing and now it's okay again, then 0 will be sent. Looking at the telegram recording, you see here marked 2 lines. The monitoring unit sends a T-Connect, you see it here, to the component 31278, which is our switch actuator, and it responds with a T-Disconnect. Everything is fine, and in this case 1 minute later the same communication will be established again, and so on. So it's a continuous process, in this case every minute. Yeah, if there is a failure, the same picture as shown before. T-Disconnect will be sent to this device, but no response possible because the component is not working anymore, is disconnected from the bus cable, so it's not able to communicate anymore. No T-Disconnect will be sent back, and of course then for the EUBS it's situation the device is not working properly anymore, and the communication group object with this group address will be sent back with value 1, indicating this device has a problem, has a failure. Yeah, how does it looks like in the real telegram traffic? You see here we have now the situation that the device, the EUBS, would like to establish a communication to our switch actuator, T-Connect. No response. It repeats 3 times. This is a traditional KNX repetition process. But the device itself tries it again another 3 times. Green, green, green here, the 3 green lines showing this. And first attempt or first repetition leads again to another 3 trials to get a connection. No result, and so on. And finally, after 12 attempts, let's say, no T-Disconnect response from the device. So the group object with failure will be sent back from the EUBS with value 1 on, as you can see here. So, and the time it repeats is here every 9 seconds around. Yeah, that's the first mode. The second mode is very similar. Polling physical address by a group object. So not cyclically, automatically by the component itself, but intentionally by any other telegram. For example, a push button or an external timer can be used for this. But the principle is the same. So we adjust in the parameters only the physical address of the component to be monitored, not different. Yeah. And we have an additional group object. And this group object, of course, has to be sent with value 1, with a group address, to start the polling. So from any push button, any timer, for example. So I can do it intentionally, not cyclically only. Yeah, in case of failure, the same principle. I have my separate communication object sending back value 1 in case of failure. Yeah, and on our picture, you see here the way of communication. So my additional sensor, whatever it is, timer or push button, sends a telegram with start polling with value 1 to our EUBS, our monitoring unit. The monitoring unit starts to establish a connection to the device with T-connect. If everything is fine, it responds with T-disconnect. If there is a failure, no T-disconnect will be sent back by the device, and of course our failure group object will be sent with value 1. Yeah, and in the telegram recording you see the same principle as before. The difference is now that we start intentionally here. You can see this telegram with our, in this case, USU, universal interface. We start the polling, and then the same procedure takes place as before. And at the end, because there is no reaction from the device, we have our failure telegram. Yeah, third mode is now via polling of group address cyclically, so we don't work with the physical address anymore. We call it so-called active monitoring. Yeah. So with this active monitoring, the monitoring unit cyclically sends telegrams via group address to the device to be monitored. And of course evaluates again this telegram, which will be received hopefully. So how to do this? You need any group object in the device to be monitored, which which can send a response to the EUBS. So for example, I take a status communication object from a switch actuator, I activate the read flag, and then I can read out the status, and the group object will send back its status. Whether it's 0 or 1, it's not a problem. It has to be a 1-bit group object where you can read out the value behind. For example, the status group object of a switch actuator. In the parameters, you only adjust here the way of monitoring your device, in this case poll group address cyclically. That's all you have to do. And of course you have to assign a group address to the dedicated group object in our EUBS, which is called send receive telegram, together to the group object of the device to be monitored, for example the status object of the switch actuator. Same group address, read flag set in this communication object of the switch actuator, and then it will be done. In our, of course, again, we have our failure group object, as always, not different compared with the other ways of monitoring. Yeah, and you see here the way of communication via group address. So our EUBS sends on this group object send receive telegram, a value read, a read request to this communication object you have used inside the device, and a value response, actual value of this communication object, 1 bit, will be sent back, and then everything is fine. And it will be sent cyclically, and for example here in this case every 10 minutes. This will be sent, and our device has to respond. It's also parameterizable within 5 seconds. So there's a bit time left until it has to respond. This can be adjusted. So here everything is fine. Response comes back. In the communication on the bus, you see it here, a read request from the EUBS, and a response, in this case is value off, from the switch actuator. Yeah, if there's no response, similar principle as before. We have our communication here with the same group address, but there's no response possible from the device, and then of course our failure group object will be set to 1 again. And the way of communication, or the telegram on the bus, is very similar. It starts here. So there is no response from the device. It repeats 3 times. The device itself repeats again 3 times, so in total 12 attempts. And then finally we have here again our failure group object with value on, or value 1. Yeah, and last but not least, the fourth version or fourth mode, receive group address cyclically. Yeah. We call it passive monitoring because now the device itself has to send, the device to be monitored has to send itself a telegram cyclically to the monitoring unit EUBS. So from the EUBS point of view, it's a passive monitoring because the other device to be monitored has sent actively the telegram. So which group object has to be chosen in such a device? We need a cyclical sender in our device, which can send cyclically. And typically in most of our ABB devices, you will find the communication or group object in operation, which can send cyclically a 0 or 1 on the bus, and this typically will be used to monitor the device itself together with our monitoring unit. But there are also other solutions possible. For example, a weather station with a cyclical telegram from the wind sensor could be used as well. Of course, all these ways of operation, let me say, generate more traffic on the bus. Often you will do this. It depends on your project, but normally you will not do it every second, but maybe every 10 minutes it's enough to monitor devices. But it generates additional traffic, and this you should take into account. Yeah, we adjust here receive group address cyclically. Yeah, cycle time in this case every 10 minutes means we expect within 10 minutes at least one telegram from the device with a cyclical sender. Yeah, here you have the group object. This will be linked to this cyclical sending telegram from the device, and of course we have also here our failure communication object. It's the same as always. Yeah, and here you see a more visual way of communication. So our device sends cyclically, here in this case the in operation telegram 60179. Maybe every 4 minutes adjusted here. You can adjust this in the device itself. In our EUBS we expect every 10 minutes at least one telegram, no problem in this situation. So everything is fine. And only, okay, first of all here the way of communication, very simple. You see only the telegram, the cyclical telegram from the component to be monitored. In this case it's every 10 seconds. In this example, so nothing else cyclically. And of course, again, if there's a failure, then we have the situation that after not receiving any telegram anymore, the EUBS has to send out the failure group telegram, shown here again in our telegram recording. So anytime there is no cyclical sending anymore, and then our EUBS reacts and sends out our failure group telegram. Yeah, so 4 different ways. In principle you can choose what you want. Physical address, yeah, you can take in every case, because maybe you have adjusted in your line coupler that you block any physically addressed telegrams. So any downloads are not possible anymore intentionally. Of course, then you cannot send also the telegram poll physical address anymore, because it will be blocked as well. Group addresses will pass line couplers as long as they are in the filter table, pass always line couplers. Yeah? So in principle, we have to check a bit what is possible, but all 4 ways are leading to, let me say, monitoring of the device itself. So you can get this failure message per device, but we can assign also components to groups. We can say, okay, we are interested in a failure message if any device in the last floor is not working anymore. And this failure message will be a separate communication or group object, of course, and maybe will be sent then to your smartphone as a message. And then you can check at your visualization maybe which dedicated device is not working anymore. So 5 groups are possible. For each you have then also the option to block monitoring. So this option here, blocking, you can block the whole group, means not any member of this group will be monitored anymore. either possible. And as you can see here, for group number 1, we have here a collective failure message if any member of this group is not working anymore. Like the individual failure group objects, but now for a group only. And last but not least, you can also create a group where every device you have assigned to your monitoring unit will be inserted, so you get a collective message if any device has a problem, and then you can react maybe together with your visualization and check what's going on there. Good, so you see monitoring unit for monitoring of KNX devices and projects in some security related applications required sometimes, and to monitor KNX device itself. So with this device, not a problem. It's possible. Good, and let's come to the next device, fault monitoring unit, SMBS 1.1, detection and processing of fault signals. So first of all, fault management. I come to some more details in the next slide. Which are the typical projects where you use something like this, where you're using something like this? Very often if you have a hospital project, you have any fault management necessary. And we have done this already in some projects. So the fault processing, fault management in such a project like hospitals is possible with this solution. Think about any industrial facilities where you have any machines as well, and you need also information if anything is not working properly. Or in other commercial buildings, could be also in an office building. So in principle, any project where you need a proven solution for fault management, including a complete logic to do this, then you might or can use such a component. How does it work in principle before we come to an overview? First of all, the device detects and processes fault messages. Typically 1-bit signals. 1 bit means failure yes or no. For example, from any fault contacts linked to binary inputs in our KNX system. Very typical situation. So we need, of course, external sensors to collect all these fault messages. The device itself is only logic, intelligence, but no in and outputs. And if you look about fault signals in a building, think about any heating, cooling solutions, compressors, ventilation, fresh air has come into the room. Or you would like to monitor electrical circuits with an auxiliary contact at your circuit breaker, linked to a binary input. Could be also a very important fault message. Or think about the solution we just discussed, monitoring of KNX devices. So could be also fault in your system if an important device is not working anymore. So it could be only a telegram from the monitoring unit. So not only binary inputs, but also any telegrams can be integrated in such a fault management. Or you take a status message from a switch actuator, any important load behind. Think about our switch actuators with current detection. So you have really the feedback, is a load properly working, yes or no? Can be integrated as well. So we collect all this information, we process, but of course any action has to be taken, and typically we send out any alarm signal, any control signal, the optical or the acoustical way, for example. So any siren, any flashlight could be activated, or any flashlight on a tableau could be initiated. Furthermore, think about our telephone gateway. Also a voice message, for example, via or to your phone, to your smartphone, could be generated. The way we process fault is defined here. It's in accordance with a German standard, a DIN norm 19235. And there are 4 different ways to do this. Fault signal with permanent light. I will explain it a bit. New value signal with simple flashing light. Initial value signal with simple acknowledgement. And last but not least, the motor signal, which is a bit different, but I will show it in the next slide. So 4 different ways you can choose, but only one way of monitoring or fault signal processing per device. This picture shows you the principle a bit more detailed. We have our fault monitoring unit in the middle. up to 100 faults can be processed. So 100 telegrams, 100 signals, 100 binary inputs, for example, can be integrated. And of course, the status, is it a fault, yes or no, will be sent to our fault monitoring unit, will be processed. And then what happens typically, for each fault, an optical indication, an individual telegram will be sent out. Normally in such a solution, it's a real optical indication on a tableau. Okay, this device, or not this device, but this fault came up right now, and you can react on this, of course. And the same for all other faults up to 100. So an individual optical indication will be given for each fault. Additionally, we have a collective message. We have an acoustical and optical central indication. So if any of our 100 faults came up, we get a central acoustical indication and an optical indication, showing, okay, there's any fault, which one you have to check. Important in a fault management system is acknowledgement. Means you have to confirm the fault first of all. You have detected there is something wrong, and then you acknowledge this fault. What does it mean practically? Only the acoustical central indication will be switched off. So system knows, okay, you have accepted first of all this fault, the individual optical indication, but also the central optical indication will be still active, showing you that the fault is still existing. Only acknowledgement has been done. Yeah, and practically, as already mentioned, how do we do this? We implement this via KNX. So our fault monitoring unit is part of the solution, and we collect all our faults, for example, via binary inputs, as already mentioned. Any switches, any contacts, any momentary contacts, whether it's a normally closed or normally open contact, no problem, we can adjust this. Or, as already mentioned, the status message from any switch actuator. Here another optional solution, we have our 32-channel universal concentrator. It's like multi-channel binary input. And if you have a lot of fault signals at the same location, it makes sense to use such a device, for example. Or, already shown before, our monitoring unit for KNX devices could be also part of our fault situation. Yeah, and then you need any, could be a push button, for example, to acknowledge the fault, as already mentioned. Yeah, and then the device, in case of fault, has to alarm, send out any signaling, any alarming. Flashlight siren, activated via switch actuator, for example. Also the 32-channel device, the UKS, can be programmed as outputs the channels, and you see you can also light up any signal lamp, for example. And if you want, take our telephone gateway for any remote alarm via voice message, SMS or email, either possible. All these signals or telegrams are 1-bit telegrams from the inputs as well as to the outputs. Yeah, let's have a look to the real logic of these 4 types of fault monitoring. I start here with the mode fault signal with permanent light. Let's have a look. Here's a diagram with 2 fault signals, fault signal number 1 and 2. And of course, for each we have an individual optical indication. We have the central and acoustical indication, and we have this acknowledgement. So let's start. Fault signal 1 appears here. Immediately the optical local indication will be activated, as well as the central ones. So then, okay, you have seen there's a fault, you go to your acknowledgement button, you acknowledge the fault. What happens? The central acoustical alarm will be switched off, as already mentioned, but the other optical alarms are still active, as long as a fault exists. Now you shut down the fault, and of course there is not any optical indication anymore. Everything is okay so far. Here an example again with fault number 1, but only for a short time. So the fault is very short before you can acknowledge. The acknowledgement is later. Of course, as before, all fault indications will be active, individual and central, optical and acoustical one. And only if you acknowledge this fault, then you reset everything again. So acknowledgement is a very important part of the solution, as long as you did not acknowledge, the fault is still active for the system. Here a combination of two faults, so we have again fault number 1 and a bit later fault number 2 appears. Of course we have our individual local optical indication as well as for fault number 2, central one as well. Yeah. And here you acknowledge your fault. Of course, fault number 1 is still active, only fault number 2 will be reset. And only if you shut down fault number 1, then it also goes down to 0 as well here in the optical and the local optical and local central, central optical indication. You see, it's a clear diagram, clear logic behind how it works. Let's go to the next one, new value signal with simple flashing light. I don't go into all details right now, but you see the difference here. We talk about a flashlight now, not about a permanent light as an alarming. So, if fault number 1 appears, it starts with a flashlight. And we will see later on there are separate communication or group objects for flashlight. Necessary. Yeah. When you confirm the fault, but the fault is still active, as you can see here. So here we confirm, but the fault is still active. Then it goes to permanent light here. That's the difference. So confirmation will be shown via permanent light. Not yet confirmed fault will be shown via flashlight. That's the main difference here. This can be extended. Third one, initial value signal with simple acknowledgement. What does it mean? The difference is that only the first fault will be shown with flashlight. A second fault, we see it here. The second fault appears here, but the second fault, you see it? The only difference is here that we have no flashlight here for the second fault anymore, because it's not the first fault, but the second, and this will be shown with a permanent light only. So it allows you to distinguish between the first fault and further faults, if there is a kind of chain, a fault chain in your system maybe. Yeah, and number 4, so-called motor message is a bit different. Motor message, or the motor signal, indicates with a flashlight again and acoustic signal if a set point state, for example, actuation of a switch actuator, does not correspond with the actual state. For instance, feedback contact of equipment. So, in other words, let's make an example. You have a motor connected to a switch actuator. Switch actuator allows you to have a status feedback. Via current detection, you have a real status feedback. Is the motor working? You switch on the motor, but due to any reason the motor does not start or is overloaded or is switched off due to any over temperature. The status feedback will be different from your switch on command. So there is a mismatch between set point and actual state, and then of course an alarm will be sent out from this device. Yeah. So we have here this example. We switch on. Of course, everything is fine. The status will be sent back as well. But due to any reason, the motor will be switched off. And immediately it goes from permanent light to optical indication to flashlight. Yeah? So that's here kind of logic in this so-called motor message monitoring way. So you can adjust for these in each device one of these 4 modes for different ways of handling your faults. Yeah, some more features around this product. Again, you can connect up to 100 fault signals, either via binary inputs or via any telegrams coming from any other device. If you have 100 fault signals available, that is available for the first way of fault monitoring, you can split this into 5 groups, up to 5 groups, each 20 fault messages. Means you have now 5 independent, let me say, logics to handle fault messages. But you can create also 2 groups with 50 messages, for example, so you have some options to split this. If you do not need so many, but many faults in one fault management, but many independent ones. Yeah, as already mentioned, typically we use our binary inputs to collect any fault signals from any contacts. If you look in the manual of our binary inputs, BES, you will find a special chapter handling fault contacts with this device. And we have some special parameters, some recommendations how to adjust the parameters. So it's a real, let me say, complete solution together with a binary input and our fault monitoring unit to have a professional fault management available. Yeah, finally some small words around the group objects and some parameters. I mentioned already that we have these independent group objects for permanent light in case of any failure or flashlight. Yeah? So, for example, the flashlight itself you have to implement in an actuator. You know, our switch actuator can create flashlight. But as you have seen, we have different situations. Once we have a permanent light, once a flashlight, and of course we need there two different communication objects to have different signaling in your system available. Yeah, and here a small overview of not all, but of the main group objects. You see here for each fault signal we have a fault input, we have an own local fault message available. Yeah. Sorry, this is a communication to the binary input, of course, the connection to the binary input, for example. And here we have our indication, local optical indication for fault number 1, and so on for all the other faults. Here's a central indication, optical and acoustical, and the acknowledgement. Yeah, and then there are two other communication objects, data loss and update. What does it mean? Data loss indicates that after bus voltage recovery, either at least one fault message input object has not yet received a telegram, or the response telegram has not been received after polling. Yeah? So, of course, worst case, your bus system is failing, so shut down, recovers, and then, of course, you would like to have the actual status of all your faults. Yeah? And we see it on the next slide. We can pull then all the inputs to get the actual status. And if not all inputs, all input group objects will send back or will receive a telegram, then we have lost any communication. So that will be indicated via data loss. So we know, oh, we do not have all feedbacks we need. And you can initiate with this communication object an update again, means you start polling again. Maybe it was only a problem due to telegram traffic on the bus. And if this communication object data loss sends back 0, then everything is fine. Yeah, and you see here some parameters which have to do with the function I've just mentioned. For example, here, inactive wait time after bus voltage recovery. What does it mean? After bus failure, of course, it takes time for all the devices behind to start up. So you can say, okay, the first 20 seconds after bus voltage recovery, I do not evaluate any telegrams, but after 20 seconds I expect that every device is working properly. And typically you will then, after bus voltage recovery, start polling via the bus all the assigned inputs to get the actual values, of course. Yeah. Good. That's about fault monitoring unit. A bit special, this component, but again, keep in mind, if you need something like this, we have a solution with our products here, together with the binary inputs. It's a proven solution for fault monitoring. Okay, I would hand over now to Jürgen. Jürgen will continue with the last device, the data logging unit.
Hello and welcome to the second part of this webinar. My name is Jürgen Schilder. I would like to continue this webinar with our device number 3, the so-called I have to change here this next slide. So, with the so-called data logging unit. Firstly, let me start with some examples how to use the device, application fields, for example. One of a very nice possibility to use the device is to record the operating life, for example, of your fluorescence lamps or halogen lamps or LEDs or something. This device records, or for example counts up the operating time, operating hours, and when we reach, for example, limit after 5 or 10,000 hours, we get an information because we reached a threshold, and then the device sends a kind of message, alarm message, to our visualization or via email, SMS, that we have, for example, to replace the fluorescence lamps or to do the maintenance. We can use, for example, this feature in all our office rooms, like in this example, or we have one reference office, yeah, and to record or to count up the operating hours in one of this office, and then we know, okay, in all this office on the same floor, maybe we have to replace these fluorescence lamps. Another application field is, for example, to record the switch on type, the switch on times of pumps or motors, for example, in heating or cooling systems. So every time, for example, the motor switches on, we count here the switch cycles, and then after maybe so many thousands of switch cycles, we get the information that we have to do the maintenance. Another possibility is also, for example, to record the operating duration of motors in escalators or elevators, also for maintenance. So we record this, the hours, and depending on so many thousands of hours, we get the information depending our threshold, and then we can plan, for example, here the so-called the maintenance that we have to organize, the housekeeping that they have to do here the work. Or, for example, in kind of ventilation systems or in fans and blowers, then we have the information depending on the operating hours that we have, for example, to replace the filters or to clean the filters when we reach here also our limit. With this device, the Data Logging Unit BDB, we can totally count up, or we can detect, or let me say count up to 35 different channels of switch actuators or also DIM actuators. Why not? We need a 1-bit information, 1-bit, for example, status information, which is sent here from a switch actuator, also a DIM actuator. So maximum 35 channels per device, and in each of the channel we can detect, or we can count the operating hours and at the same time also the switching operations. So both of these operating hours and switching operations are now here detected per channel. So individual, also per channel, we can specify how we want to count. Maybe we can start from 0 and then we count upwards. So the value now operating hours is zeros, and then he counts 1 hour, 2 hours, 3 hours, up to 100,000 hours, for example. Or the other method is, we start from a set value, maybe 50,000 hours, and then we count downwards. This is also possible. So per device, per channel, we can select this kind of counting method, or the other one, for example, the downwarding. So, and then we have as a 4-byte value on our KNX bus, the value here of our operating hours or the switching cycles. So we can see this value maybe here on our touch panel or on the visualization system. Additionally, we can work with thresholds, a very nice feature. So we can set here thresholds. When we, for example, count upwards, then we start from 0, and then we can set a threshold 1000 hours, and if we reach this 1000 hours, the device sends a 1-bit kind of alarm message. Additionally, we can use the feature when we count downwards, then we start from our maybe set value, and when we reach the value 0, then the device sends out the alarm message. Later I will show you here the examples via some pictures. So a very nice feature is that we can change these thresholds or our initial values by sending a KNX telegram. So in the ETS we set some default values and we do the download via the ETS, but later during normal operation we can change here our thresholds by sending a 4-byte value per channel individually. So the ETS allows to program all 35 channels together or individually. So this is one of the first questions. Then we can, when you use this parameter, then we can change individually all our 35 channels. The operating hours, they will be sent cyclically, it's a parameter, or after they have changed. The operating hours internally is counted every seconds, but the output telegram to KNX is in hours. So now when an hour now is full, then he sends it, for example, here, depending on the parameter. So the switching operation or the cycle telegrams, for example, they can be only sent cyclically. So now what happens when we have a bus voltage failure? Of course, all the values, our operating hours or the switching operations and our thresholds, all these values are of course stored inside the device, and they will not be lost. So this is really inside, so do not fear, the values are still inside the device. Additionally, we can write a short text description to all our 35 channel. So it helps you maybe for the documentation, or when you hand out a printout to the end user, then you can write maybe, for example, channel number 1 is the fan in this room, in this floor, and so on. So it's really a good thing to have an overview of all the 35 channels. Additionally, it's also possible that a data logging unit, for example, send a command to the switch actuator, maybe to read out whether the output is switched on or off. We can do it cyclically. This is also a parameter inside the device. But do not forget, then the read flag must be set in our status object of the switch actuator, because the device here, the data logging unit, is expecting here then an answer to the read command. So here we have the first parameter of our ETS window. Let me say here the general parameter. Then you can set here, for example, the first parameter. How would you like to do the parameterization individually for each of the channel? Or when you tick it here, then you have all settings for the complete device. Do the same. So then we can set here, would you like to send the operating hour cyclically, yes or no, or the switch operation telegrams, and for example, there's the time for the cyclical sending. This is here in the menu general. So in the channel designator, here we can write a short text description to all our 35 channels. For example, here, our channel number 1, we can write here a clear text: fan in our meeting room, for example, in the floor number 2 in the room 112. Or here, channel number 2, this is the pump and the chiller for the cooling in the east wing in our basement. So this is only for documentation. This is not sent via KNX, for example, via the bus. This is only here when you hand out, maybe at the end, this documentation to the end user. So then we have the parameterization of all these channels. Now I selected that I want to change to the settings individually. Then I click here, say channel number 1, and I get all the parameters here for my channel number 1. When I have done it, I can choose here the next channel, up to channel number 35. So then I have here my parameters, for example, which belongs to my channel number 1. What should happen when I make a download? Should I want to overwrite, for example, the counter values inside the channel 1? No or yes, for example. Or it is possible to change maybe the limits or the thresholds via KNX telegram? No or yes. That's what I can select here. So in the next row, I have here the parameters about the operating hours. The maximum limit of operating hours can be 100,000. This is the maximum value of the operating hours. So I can say when he should start counting, for example, with an on telegram or off telegram. So we can count how many hours are the lights on or how many hours are the pumps off. It is maybe also important. So additionally, here the parameter how we want to count, which method. Maybe, for example, the total running time. So we start from 0 and then we count upwards. Or the remaining run time. So we start, for example, from a start value and then we count downwards. This is here, for example, depends on these two parameters. When we want to use the threshold, then you can write here what is the threshold, maybe 1000 hours. And then when we reach this value, 1000 hours, the channel number 1 send the alarm message to our KNX system. So here we have the parameters for the switching operations. The maximum limit of switching operations now are here 4,294,967,295 switching cycles. This is a lot of numbers because we have a 4-byte telegram. That's why we have here up to 4 billions. And here the same question, how we should start counting when we switch from on to off or from off to on our operating cycles. Again, the method would we like to count upwards or downwards, and here the threshold, how many switching cycles then we want to have our alarm message. So here we have the screenshot of the ETS group objects per channel. Here channel 1. Per channel 1, I explain it later in more details. So, but we have also 5 group objects which belongs to the complete device. One is, for example, here the group object 245, which is the name recall all switch positions. So what does it mean? Here when we send the logical one, maybe via a time switch or via a sensor, then the device sends read requests to all our switch actuators or DIMM actuators and reads out whether the switch actuator is switched on or off, only to update maybe, for example, here the values per channel. So the next parameter here, the next group object, we can maybe send also a 1-bit object, and when he receives here the value 1, then the device answers with all 35 channels, including per channel the switch operations, how many, the numbers as a 4-byte telegram, the operating hours each of the channel has at a moment, and each of the channel if there is the alarm on or which the alarm here for the switching operations and the alarm also here for the operating hours. These are here the 1-bit informations. So with the next object, the so-called enable, delete or override, we can trigger or we can start a time slot with up to 10 seconds. So, and then during these 10 seconds, we can send another command, 1-bit with the value 1, to this object delete all operating data, and then, for example, all the values are resetted to 0 or to our start value. To prevent that this happens, so you have to do 2 things. At first, send here 1, enable the time slot, and then send here another telegram. It's also possible. Or it is also possible, for example, to delete the values of each of our channel. Then you have also to enable here this time slot by sending a 1, and then you have to send the value 0, for example, to the channel number 5 or channel number 8 of the operating hours. So it's also possible to delete or to reset all the values per channel. You see here, this is the object delete all operating areas. So all numbers, for example, are now resetted, but before you have to enable it by a 1 telegram. And of course, the last group object is here the in operation, like each KNX device has it, for example. So the device can send cyclically, maybe to KNX, the logical a value that he is still alive and he's okay. Maybe you want to monitor this device via the monitoring unit. So what about this operating hour? Remember, we can the maximum value are here 900,000 hours. So we can he measures or he counts internally each of the channel in seconds, but the output telegram is still in hours. So it's a 4-byte telegram. And when we switch on or switch off, he counts here our the operating hours, the operating time, or always. For example, this is possible. And you have seen it before in the ETS. You can choose here the method. Would you like to count upwards or downwards? And if it's allowed to change here, maybe the thresholds or the initial values via KNX, yes or no. So here's the overview. How does it work? When you use, for example, this parameter total runtime, then we start here from 0. This is our start value, 0, and then the device is counting upwards. So the maximum value is here up to 100,000 operating hours, and via KNX, a 4-byte value, you can see here at the moment how many operating hours the device now has worked. When you want to use the threshold, then you can specify, can you set inside the ETS a threshold value as a default, and via KNX it is also possible to change here this threshold. And now the device starts counting the operating hours, and when he reaches here our threshold, then the channel send here alarm message, the logical one, maybe to trigger an alarm or to pop up a window in your visualization or on your panel, or send an email or SMS, for example. So this is one of this method. The other one is we use, for example, here the remaining runtime. So inside the ETS we set a start value, which can be maximum, of course the 100,000 hours. So and then he's counting downwards. And when the device reach the value 0, then the data logging unit per channel sends our alarm message. And also here via KNX, it's a parameter to change, for example, here the threshold. So you can choose what you want, what do you prefer, which kind of method. So the communication, the group objects per channel. At first we have here the so-called switched position received, which means the device or the channel must know if the actuator, switch actuator, dim actuator, the status is on and off. So with this object we have to link it here with our actuator. So the next object here is our operating hours as a 4-byte. Here we can see the operating hours, the counted values, of our switch actuator. How long, for example, is a switch actuator on, or how many hours stopped, for example, here your pump or something. Remember, these are here hours. Internally, the device counts in seconds, but the output telegram are here now in hours. So, for example, via the next object, the start limit value, we can read out, for example, our thresholds, which we have set as a default in the ATS, or via a 4-byte telegram, we can change here the threshold. This threshold per channel is also possible here. And the last one, operating hours alarm. Here, if for example, when the operating hours has changed our limit, our threshold, then he sent here the alarm message, the logical one. So here's an example. Here in our installation we have switch sensor or a time switch, brightness sensor. With rocker 1 we switch our output A. The channel 1 of this time switch also channel A. So here we have linked a lot of group addresses. So but we have only one group address here in our object status switching, our 0537, which gives us exactly the status of our output A. And we link this group address here to our channel number 1 to the object switch position. So the channel 1 knows exactly when the switch actuator is switched on or off. When it's switched on, then he starts, for example, and count upwards our operating hours. And here with this object, operating hours, the number, we can see exactly this value here on our KNX panel, for example, or visualization. Now when we want to change, for example, the value of our threshold, then we can send it here as a 4-byte value to this object, start limit value change, for example. And now when the device reached the specified or the threshold, then he sent here via this communication object the logical one as a kind of alarm message, and we know we have to do maintenance to replace the filter or so on. So we have nearly the same principle also for the switching operations. We can detect it, of course, per channel. As a parameter, we have to set when we want to count from off to on or on to off. These two possibilities we have, and again the same, how we want to count, upwards or downwards, or is it allowed per channel to change the threshold or our initial values via KNX, and what should happen when we make a download, should the values be overwritten, yes or no. So and here we have again our method when we want to count upwards, for example, upwards, then we start here from our initial value, which is 0, and then each of our switching cycles we count here, and the maximum value of switching cycles or switching operations now here are 4 billions, more than nearly 4 billions. And the same, this threshold, we can set it as a parameter at the ETS, or when we allow it, then we can change it also via a KNX 4-byte telegram. There's the other way of counting the remaining value. So we start from a value which is also set in the ETS, and then the device counts downwards. And then we see, okay, for example, we have maybe 100 or 1000 cycle times, then we have to do maintenance. And now when we reach here the value 0, then the device sends our alarm message as a 1-bit information to KNX. So we have also to link our channel number 1 to the status object of our switch actuator or dim actuator via 1 bit. Then he has to know, because then he knows if the output is on or off. Here as a 4-byte value, we get the number of our switching operations up to our 4 billions. This is only the number. And when you want to use the thresholds, then for example, we can see here our default threshold value. We can read it out, or via KNX telegram, then we can change here our threshold. And at the end, the last group object is here the same, our alarm object. So now when he counts downwards to 0 and he reached the value 0, then he sent our 1-bit alarm message, or when we count upwards and he reached our threshold. Good, here's the principle of the switching operations. Again, like before, we have sensors, like push buttons or weather stations or brightness sensor. They send all the informations, the commands to the switch actuator, and one status group address which is linked here to our data logging unit. And then when he switched from on to off or off to on, then he starts here counting upwards or downwards our switching operations. We can see the value as a 4-byte on our touch panel, or on the visualization. We can see also read out, or we can change here the threshold value, and again when it reaches threshold or we count up to 0, we send here, the device sends here the 1-bit alarm message. Good, so far the introduction of these 3 devices. I would like also to recommend you to visit or to attend the webinars of the KNX Association. Visit the website knx.org, click on the menu Training, KNX E-Academy, Webinars. So you can also take part on these webinars. It's also very nice. The KNX Association introduce here, for example, the ETS apps for the ETS 5 and so on. Good, let me check the chat at the moment. We have no questions. Oh, okay. You will still get also the feedback email, including the presentation of this webinar, the recorded file, of course, like last time. And when you have still some questions, you can write an email to Thorsten or me. So we will still answer it. So now it's summer outside. We will have also a summer break here in Germany. I hope you will have the same in your country. So also our webinars will have a summer break. So we will continue with the next webinar, the same on Wednesday, the 23rd of September. So the same time, morning 9 o'clock German time, and afternoon 3 o'clock. So the topic of this next webinar now will be our new IP devices. So we will launch soon a new IP router, the IPRS 311, and IP interface IPSS 311. So far, I think we are at the end of this webinar. We would like to say thank you for attending the webinar, and we're looking forward to welcome you again on the next webinar, the 23rd of September. Enjoy the summer break. Goodbye.
Bye-bye. Ciao.
Bye-bye.